Hello and welcome back to Honors Topics in Physics. Since some machines we dealt with some rotation of levers and pulleys and things like that, we're going to talk a little bit about rotation in general. Lots of things rotate around you, so it's worthwhile knowing a few things about that. So first off, when something is rotating, we've got what's called the axis of rotation, which is an imaginary line that goes through the center of the rotation. The points that are on the axis of rotation, the points of that object, don't appear to be moving. They're stationary. And the part, as you get further away from the axis of rotation, the parts start moving faster and faster. So the parts on the axis of rotation appear to be fairly still. So here I've got a little object I'm going to rotate, and you can see that through the middle of this appeared pretty stationary. And the axis of rotation would be a line that's running into the screen in 3 dimensions. So again, it's moving the least right in the very middle, so the axis of rotation would lie in the middle. The axis of rotation doesn't have to be right in the middle. I can fix it with a pin or something, and now you can see the axis of rotation is this dot here, not in the middle. So if the axis of rotation goes through the object, we call that rotation. If the axis of rotation is outside of the object or it is revolving around something, we say that that's a revolution. So rotation and revolution. So what does the Earth do? Well, the Earth rotates on its axis, which causes what period of time? Minute, day, hour, second. And that causes that's what defines the day, okay? And it also revolves around the sun, and that's what causes the year. And it does both at the same time. All the planets rotate at some different weird angle. So here you've got the Earth. You can see its axis of rotation is slightly tilted. Here we've got Mercury, Venus, which is the axis of rotation is pretty much vertical. The same with Mercury. And then we had Mercury, Venus, Earth, Mars, I guess that's Uranus. That the axis of rotation is almost perfectly sideways. And that just depends on how they form. So does a figure skater revolve or rotate as they spin? Well, if it's one person, then they are spinning about their axis of rotation, which goes through their core, their body core, their center. So anyway, they're rotating. So we've dealt quite a bit with linear speed. We've got slow and fast linear speed. There's also rotational speed. We can have slow rotational speed or fast rotational speed. And we can talk about the units on that a bunch of different ways. We can talk about rotations per minute, rotations per second, degrees per second, radians per second, all kinds of different units to measure that. So when we talked about linear distance, we use meters per second as our primary unit. In this class, we're going to talk about rotational speed and rotations per second. That's just going to be satisfactory for what we do. Very commonly, you'll see rotational speed measured in RPMs, which is rotations per minute. All kinds of things, anything that rotates is probably going to be measured in RPMs. So the tachometer on a car, which measures the rate at which the engine is running and doing its cycles, is measured in rotations per minute times 1,000 on this meter. So this is the tachometer, the speedometer, and then the other meters. Record players have a certain RPM that they run at, and that sort of thing. So a record player makes 100 complete rotations in 25 seconds. What's its rotational speed? Okay. Well, we're looking for rotations per second, which means we want our rotations number up top and our seconds number on bottom. So it'd be 100 rotations divided by 25 seconds gives us 4 rotations per second. So that means in 1 second, this thing makes 4 complete rotations. What would it mean if an object had a rotational speed less than 1 rotation per second? What would that mean? Well, it would just mean that in 1 second it didn't quite make it all the way around. So this one made it 3/4 of the way around in 1 second. but it would make it around all the way around in another fraction of a second. Okay. DVDs, which are dying media now, operate at about 900 RPMs. So we could convert that into rotations per second if we wanted to, by dividing by 60, and that would give us the rotations per second. What would that be? 900 divided by 60, 15 rotations per second. So that's spinning pretty good. That's a pretty good clip to make that number of rotations. So how many rotations would it make in 10.5 seconds? Well, if it's rotating at 15 rotations per second, and I want to know how many rotations it makes in 10 seconds, I'm going to multiply that 15 times 10.5, and it'll make 157.5 rotations in that amount of time. Okay? So when something is moving around in a circle, it does have a meter per second speed. I mean, it is moving meters. It's traveling meters in time. So and that speed is called the tangential speed. So we're going to talk about the tangential speed and then the rotational speed, and they're separate things. Okay, so that has both a tangential speed and a rotational speed. Notice that the tangential velocity is always tangent to the circular path that it travels. If you've learned about tangents yet in geometry or algebra, math class, that sort of thing. So it just basically means a line that kind of kisses a curve. Okay, so if we've got two ladybugs on a record, which is what the book likes to talk about, and we give the record a spin, and I were to say compare the rotational speed per each dot, and you can bet that these would be some multiple choice questions along these lines. So which dot is making more rotations per second? Well, they each make one rotation in the same amount of time, so their rotational speed is the same. Okay, they both complete a rotation in the same amount of time, so their rotational speed is the same. But if I compare their tangential speeds, okay, which is their meter per second speed, okay, doesn't the outside dot have to travel a greater path in the same amount of time as the inner one? Okay, which means that this one travels more meters per second, so it's got a greater tangential speed. Okay, so same angular speed or rotational speed. The outer one is always going to have the greater tangential speed. Okay, I already kind of covered that. So what determines the tangential velocity for objects on a fixed object that's rotating is the distance from the axis of rotation. So the further away you get from the axis of rotation, the greater your tangential speed is going to be. Okay. All right. So let's see. Do the dots have the same radial distance? Do they have the same radii, or is one further away than the other? Well, it looks about the same. Okay. So what about these? Do they have which dot has the greater tangential speed? Okay. Which one is traveling more meters per second? Okay. Well, they're traveling the same circular path, but this one is traveling that circular path more quickly, which means it's got a greater tangential speed. Okay. What about rotational speed? Okay, which one would have the greater rotational speed, or would it be the same? Okay. Well, the one on the right is making more rotations per second, so that means it's going to have a greater rotational speed. Okay. The equation for that relates to tangential speed and rotational speed is this. The tangential speed is equal to the r, the radial distance, the distance from the axis of rotation, times the rotational speed. You can jot this equation down if you want, but we're not going to be using it for any sort of math, because in order for the numbers to work out right, this rotational speed is going to be measured in radians per second, which we're just not going to mess with. Go into radians per second. It's just not really worth going through. So we're just going to use this as a guide to thinking. And the guide to thinking is basically, if the rotational speed is the same, the further away I get from the axis of rotation, the greater my tangential speed is going to be. And you don't even need this equation to remember that. So, so a spot moves fast on a record when it's spinning fast, which means we have a great rotational speed, okay, and when it's far away from the center, when our radial distance is bigger. Okay, so now if we were to double the rotational speed of the object, okay, how would the tangential speed of an object on that record or whatever it is? If we double the rotational speed of a record, how does the tangential speed on that record of a ladybug compare? Well, if I double this rotational speed, I'm going to double the tangential speed. Okay. So let's see. So here we've got two dots on a record player. If the blue dot is twice as far away from the red dot, then its tangential speed is. So if I double the R, okay, and keep the omega the same, because they have the same rotational speed, they make the one rotation the same amount of time. But if I double this R, what's that going to do to the other side for the blue one? It's going to double it as well. Okay. So if I'm twice as far from the axis of rotation, I have twice the tangential speed. Okay. So here we've got a meter stick that's moving at some speed, let's say 2 meters per second. How fast is the 90 centimeter mark moving? So this is my axis of rotation here. So this is 30 centimeters away from it, and this is 90 centimeters away from it. So if this is 3 times as far, which it is because it's 90 instead of 30, this is 3 times as far, it's going to have 3 times the tangential speed. So instead of moving at 2 meters per second, it's going to move at 3 times that, or 6 meters per second. Okay? Let's see. A record player spins at 5 RPMs. One penny is placed a centimeter away from the center of the record. Has a tangential speed of 2 meters per second. What will the rotational and tangential speeds of a penny placed 3 centimeters away from the center be? Okay. So we've got 2 pennies that are on the same record, which means they're going to have the same rotational speed. Okay, so they're both going to have a rotational speed of 5 RPMs, or whatever that is in rotations per second, but it's fine to keep it in RPMs. Okay. Now, what's going to be different is the linear speed. So the penny that's 3 centimeters away is 3 times as far away from away as the other penny. So its tangential velocity is going to be 3 times as much, which would be 6. So the rotational speed will be the same. That'll be 5 RPMs, and the rotational and the linear speed, the tangential speed of the outside penny will be 6 meters per second. Okay. So what would the linear distance? What would be the total distance traveled by each one of these dots in one rotation? Okay. Let's just look at the red dot. Okay. Well, what they're going to travel is the circumference. So if you figure out the circumference, you need 2 pi and the radius. Okay, so if I know the radius, which I do, the radial distance is 0.25 for the red one. Okay, then the circumference is 2 pi r, so 2 pi times 0.25. Okay. Which we'll get into that more in a little bit. So let's say that you wanted the most excitement on a carousel ride. So you're on a merry-go-round. Do you want to sit towards the middle, the inside of the merry-go-round, or do you want to sit towards the outside of the merry-go-round to have the most excitement, as exciting as these are? Okay. You want to sit on the outside because you're going to have a greater radial distance, which means you're going to have a greater tangential velocity. So you'll be moving faster. Okay. All right. So a wheel can both rotate, okay, and it can move linearly through space and time. Okay, so it can both rotate and move linearly. A wheel which is rolling across the ground does both at the same time. Okay, it does both. It's rotating and moving through space and time. Okay, so if a wheel makes one rotation, okay, how far will the wheel have traveled? How far will the center point of the wheel have traveled? Okay. Well, what it did on this floor here is it traced out its circumference on the ground here, and as soon as it got back to that dot, that was one rotation. Okay, so And if a wheel makes one rotation, it moves a distance equal to its circumference, and that's something that's important to know. Okay, so if a wheel doesn't skid, which we're not going to deal with any skidding wheels, and a wheel moves a distance equal to its circumference in one rotation. Okay, so here we've got a problem. A wheel on a bicycle travels 4 meters across the road. If the radius of the wheel is 0.25 meters, how many rotations does the tire make? And if it does this in 5 seconds, what's the rotational and linear speed of the bike? Okay, so obviously we're going to be taking into account what we just learned, the fact that for every rotation, the bicycle travels one circumference. So the first thing we're going to do is we're going to figure out the circumference. So 2 pi times 0.25, so which is the radius. So it gives us 1.57 meters per rotation. Okay, and then to figure out how many rotations it makes, I take the 4 meters, which is the distance traveled, and I divide it by 1.57, the circumference, meters per rotation. So you take the total distance and divide it by the circumference, and that gives you the number of rotations, so 2.55 rotations. The next question is, if the bike crossed the road in 5 seconds, what was the rotational and linear speed of the bike? Okay. Well, to figure out the rotational speed, we know it made 2.55 rotations, okay, divided by 5 seconds, and that gives us 0.51. Okay, there's my little symbol for rotational speed. That's not terribly important, but I'm going to make a note of that. It looks like a W. You saw that on that equation, Vt equals R omega. It's really a Greek lowercase omega. And the linear speed, we take its linear distance that it traveled, which was 4 meters, and divide that by the time, which is 5 seconds, and we get 0.8 meters per second. Okay? Alright, so what I want you to do is do worksheet 7.3.5, and that will do it for today.